Hi, this is Mrs. LaBarbera. This is Physics Chapter 12, Sound and Light, Video 2. Today's topic is electromagnetic or EM spectrum. The objectives are: no, all EM waves are produced by vibrating charges. They are transverse waves and travel at the speed of light c in vacuum or air. Understand the relationship between speed of light in a vacuum, frequency, and wavelength of EM waves. Understand how optical density affects speed of light. Be able to determine an EM wave's type using EM spectrum chart. The electromagnetic spectra. Electromagnetic waves are transverse waves which are capable of traveling through a vacuum. Electromagnetic waves are produced by vibrating electric charges. They consist of both an electric and magnetic field at right angles to each other. So the direction of travel is also perpendicular to the electromagnetic directions. The alternating electric field creates an alternating magnetic field, and the alternating magnetic field creating alternating electric field. That's why they can depend on each other to propagate. That's why they don't need any medium. EM wave types. EM waves are classified according to the methods by which they are generated or received. So there are radio waves, microwaves, infrared, visible light, ultraviolet, X-rays, and gamma rays. So all these are listed on your reference table. So the radio waves has highest wavelength and has the lowest frequency. Remember, they all travel with the same speed. So the radio waves has the lowest frequency. On the other hand, gamma rays has the highest frequency. You see, wavelength and frequency are inversely related because all the speed are the same. So the size of the radio waves is about a building, microwave, honeybees, infrared, about a pinpoint, and so forth. So they are the higher you go, the higher the frequency and the smaller the wavelength. So the temperature of body emitting the wavelength is getting hotter and hotter as the frequency increases and wavelength decreases. Remember, electromagnetic radio waves are not sound waves. Even though we hear radio like sounds like radio is sound, but it's not. Radio waves are not sound waves. You have to remember that. Now that's the most familiar waves, electromagnetic waves is light. So visible light and electromagnetic transverse wave is a very, very narrow band of wavelength in EM spectrum. So visible light consists of wavelength from approximately 700 nanometers to 400 nanometers. This narrow band of visible light is affectionately known as Roy G. Biv. So each individual wavelength within the spectrum of visible light wavelength is represented by a particular color. So here is a short wavelength, you have violet. On the other hand, longest wavelength is red. So again, red has a longer wavelength, smaller frequency. On the other hand, violet has shorter wavelength and bigger frequency, higher frequency. Speed of EM waves. All electromagnetic waves, including light, travels at the same speed, 3 times 10 to the 8 meters per second in vacuum or in air. So this also in the reference table. The speed of light in vacuum is represented by symbol C. The speed of light is slightly less than in air is slightly less, but we can assume it to be the same when we do calculations. The speed of light in vacuum is the limit of the speed of any material body. So nothing can travel faster than the speed of light. Speed of light also equals to F times lambda, frequency times the wavelength. So as you can see in air, we know frequency doesn't change. It's always same as the source. So when the wavelength speed decreases, wavelength decreases. So compared to the speed of microwave in vacuum, the speed of radio wave in vacuum has to be the same. Remember, radio wave is EM waves. Another example, how long does it take light to travel from the sun to Earth? So this one is asking you the time. We know V equals D over T because light doesn't accelerate. Okay, so we use this equation. So for T, we can switch T and V. T equals D over V, divide the two numbers, you have 500 seconds. So that's about 8 minutes. Optical density affects light speed. So an electromagnetic wave is produced by a vibrating electric charge. As the wave moves through the vacuum of empty space, it travels at a speed of c. When light wave moves through a medium that is not vacuum, its speed slows down due to its collision with particles in the medium. So the speed of the wave depends on the optical density of that material. The optical density of the medium is not the same as physical density. So one indicator of optical density of the material is the absolute index of refraction value of the material. These values are also listed in your reference table. So absolute index of refraction N is the ratio of the speed of light in the vacuum to the speed of light in that material. So N equals C over V. As you can see, N would be 1 because V is C in vacuum, right? So the absolute index of refraction has no unit. Like another value, coefficient of a friction has no value. So is the absolute index of refraction because it is a ratio of the same quantity, speed over speed. The greater the value N, the denser the medium, so the slower the light will travel. The slower it is, the shorter the wavelength. So one thing, because N equals C over V, that means N times V equals to C. So the product of the absolute index of refraction of a material and the speed of light in that material, V, always equals to 3 times 10 to the 8th, which is a constant. Let's take a look at your example. Check your reference table. In what material is the light travel slowest? So look at your reference table, find the biggest N. So in this case, biggest N is diamond from the reference table. And the light travels fastest, which is vacuum or air. The relationship between index of refraction, speed, and wavelength. So the higher the index, the lower the speed, and the shorter the wavelength. So they are kind of inversely related. So inverse, but we know the higher the speed, the longer the wavelength. So speed and wavelength are directly related. But the index of refraction is inversely related to the speed and inversely related to the wavelength. So as EM wave travels from one medium to another, remember what doesn't change is the frequency. Frequency remains constant, always the same as its source. But its speed changes, and as a result, wavelength changes. Let's do a couple of examples. What is the speed of light in a medium with index of refraction of 2? So N equals C over V. V equals to C over N. So V equals to 3 times 10 to the 8th divided by 2. You have 1.5 times 10 to the 8th meters per second. Another example, the constellation of Orion is a highly recognizable arrangement of stars. So there are 2 very distinct stars in this constellation, Betelgeuse, which is red, the other one is Rigel, which is bluish star. The color of red has a wavelength about 750 nanometers, and the color of blue has a wavelength 400 nanometers. Which color has higher frequency? So the higher frequency is the one with a shorter wavelength. So in this case, is Rigel. The blue color and which color is hotter? So we know the higher frequency, the harder it is. So it would be Rigel. Another example, so an EM wave is traveling through outer space with a frequency of 8 times 10 to the 13 hertz. What is the wavelength of this wave? So to find wavelength, we have to use wave equation. We know all EM waves in outer space, which is vacuum, travels at 3 times 10 to the 8th meters per second. So we use V equals F times lambda, so lambda equals V divided by F. So lambda equals 3.8 times 10 to the negative 6 meters. What type of wave is this? Look at your reference table. You can find this is in infrared range. That's it for today. Thanks for watching.